skewness, through the deviation of that certain shape, we will figure out how the shape is being, how the shape is in real life, and then we'll reconstruct it. So how will we reconstruct it? We will get point cloud. So multiple points. Currently, this scanner has a resolution of 0.2 mm. So we'll get multiple points along the surface of this geometry. Then the software which we see here will post process it and fit curves and generate a mesh. So let's get started with the scanning first. So when I switch it on, you can see I went into scan mode. So here you can see there are two modes here, geometry plus texture and geometry. So texture is basically color data. Since we are using visual light, so we can also capture the color data of the surface. But let's say I want to just scan geometry. So I will click on geometry here and we'll start a preview. So you can see there is a data stream on the left side. It is showing the optimal range from where I should hold the scanner. If I'm too near, you can see it is not registering properly. If I'm too far away also, it won't register properly. So whatever I told you verbally, the like we are projecting a pattern and then we are looking at it through three different cameras and figuring out how it is curved, how the object is curved. So this is being done real time by the software. And once I start recording, the software will start stitching all these scans together to form a object. So optimally, I should keep the data stream at that green range in the center. So let's start recording. So we have started recording. So I will slightly move around the object, maintaining the data stream at the center. What the software is doing real time, it is stitching all the scans from all the angles. So I can do one thing. See, if I go too far away, it has already detected that it cannot stitch further. See, it has lost track of that object. So what we need to do, we need to go back to the last point of scan. And it will automatically recollect and start stitching further. So I will pause the scan momentarily, and then you can see I have issues going to the other side to scan the right side of the skull. So I'll just rotate it and continue the scan. We'll wait for the software a bit. Yeah. So it started scanning. If it is visible, you can see the grid pattern or the light it is shining. Currently, it's a mix of squares and circles. And we'll stop the scan here. This scanner also has its inbuilt cooling system to continue cooling the camera sensors. Now we'll see what data we have gotten. You can see we have 728 megabytes worth of data here and three separate objects. It has I will get my mouse. So you can see since we scanned at two different orientations, you can see one is the first orientation, this skull, and another one was when the skull was rotated. And I only scanned from this side, so we can only see the right side of the skull. Now we have to do post processing. So what is the basic, like you can see it's very noisy data. It has captured multiple things that we don't want, so we need to figure out useful data from here. So first we'll remove the base. We don't want the table, we just want the skull. So this is a software from Arctec company, because this scanner is the Arctec EVA, but this is standard for most of the 3D scanning softwares. These are standard tools. Arctec have their own proprietary like base selection and eraser tool. So we'll just select the base and wait for the software to recognize. So you can see the software has recognized the base and selected it, and we'll erase it. So now we have this data with lots of outliers. You can see uh, small specks in the air, which it has scanned, but it's noise. We don't want that data. So we'll go to tools, and let me show you. See, this is the second scan. You can see, you can figure out slightly the shape of a skull, and this was the first scan. But since we did not scan the right side properly, you see there are holes there. So now we need to align both these. So first we'll do the outlier removal. So you can see whatever noise was there outside of these surfaces, they have been removed. Now, one of the main points in 3D reconstruction is alignment. So how do we align two 3D like point clouds? So right now it's in like what you are seeing in the preview, it is a smoothened out point cloud. So we are fitting various curves and smoothing the surface to show you this preview. But at the core, it's still lots of points along the surface. So in a human skull, what are the markers? The nose tip is a marker. The start of the cheekbones is a marker. So we'll use these markers to align the two skulls. So let's find the nose tip. Can we find it? You can see this is a nose tip. So this was point 1. Huh. Okay. And another side we have a point cloud here. So let's hide it. Let's do one thing. We'll go to tools and align the first scan first. And then we'll work out the other things. So since nose is not visible, let's just align the top of the head with this top. And we'll need 3 points. So we'll go with the jaw, bottom jaw. Now this is right now, we are doing kind of hit and trial. You can see the software is struggling a bit. So let's align the markers. Now you can see it has not aligned that well. So can we see the nose? So we cannot. But let's first go through this alignment process. We can. And we need to align the behind. 1, 2. This one. So now we can clearly see the nose. So we'll clear markers and we'll go with what we know. So nose tip 1 to nose tip of 2. This is the second nose tip. We'll go with the top eye. This is the eye bone of the right side and eye bone of right side here. We'll go with this part. You can see the jawbone starting here. And jawbone should be somewhere here. Let's align them. Okay, we need to align the okay, we can do this also. Align this with this point. So you can see it has somewhat, where is the arrow? Aligned. Now we can just go to the automatic mode. And okay, did not work out. So this is how we go on with the alignment. We'll go back to tools Hmm? We can take the scan again, but let me just finish the fusion for this. Huh? So we'll continue the scan registration. So now we are fusing, smoothing the mesh file that we have generated. So you can see there are holes here, and we have tools to fill these holes. You can see the reconstructed skull here. So we'll go to fix holes tools, and we have a fix hole tool to fix these holes here. So you can see the bottom part, since it was covered by the base or the table, it was not scanned, so we need to fix and generate a surface there. So these all can be done by the software. So this is where it gets like company centric, so depends on which company scanner we are using, what features they provide in the reconstruction software. But yeah, alignment and fixing holes, these are like basic tools. So we'll just save it and go to home. And I can show you previous scans that we have done on this skull after fixing all the holes. So this is how the final mesh looked like. You can export it into different mesh files. OBJ is a generic mesh file you can, and PLY is the your normal point cloud file. So supports all this format. STL for 3D printing. So this was it. Any questions regarding this scanner? No questions? Okay, sir. So I should. So we try to fit a curve. Let's say 3 points are there. One point is here, one point is here, one point is there. It's like it's a triangle, right? But we try to fit a let's say a Bezier curve. If you guys know, we'll use these 3 points and smoothen it, like have a smooth surface along these 3 points. Then let's say another point is there. Then we'll try to interpolate another curve along these 3 points. Like that, it will continue as a like a serially from bottom to top, or like whatever the algorithm we choose. So that is how we, from a point cloud, we can get this smooth surface. But it depends on how we like which algorithm we use. If you don't want a smooth surface, we can just fit triangles on it. So that's how you see a mesh file. So it's a combination of multiple triangular elements. Yeah. Huh. No, so this currently this scanner has a resolution of point with that accurately. For that, you would need some like high resolution scanner for that. This handheld scanner won't be sufficient for that much accuracy. So this is like let's say I want to some mechanical parts are there or here only for obviously it can't be used for medical purposes because it is not that accurate. But let's say I want to okay for medical purposes also. Let's say I want to scan somebody's ear. I can get that dimension accurately through this handheld scanner, and then we can maybe print it with biocompatible materials. In case that person loses a ear, we can replace it with a fake one. For so that is one of the applications. So it's all like based on like this has a certain resolution. So if you have any application that does not require that pinpoint level of detail, you can work with this thing. Internal parts, because as you see we have to take the scan from different angles. So internally of course this scanner is and distance is also, you can see it tells you how much distance to keep. So and since this is a structured light scanner, you need a well lit like environment for. And problem with structured light scanners is if the surface is too shiny, it won't reflect the projected pattern properly. So the cameras won't be able to capture the deviation in those small grids. And that is the core of how this thing generates the shape. It captures the deviation of what it is projecting from three different cameras here. So if it's not able to capture that deviation, then it cannot do the mathematics to reconstruct it. So not for internal low lit environments. Yeah. No, this works purely in visible light. So anything that can reflect visible light properly, mostly matte surfaces, it will work with them. That is why it is safe to scan humans and animals also, because it won't harm your eyes. It's purely working in visible light spectrum. Parameters of what? Size as in dimensions of what? This thing, that scanned object. Yeah, after you get the point cloud, you can load it in any CAD software and scale it down, up, edit it. You can do anything. Huh. So we do this. I'm from Biom 3D lab under Dr. Samarth Raut. So we mostly work in this 3D reconstruction of like right now multiple projects are going on. So we are scanning areca nuts and getting the surface mesh and trying to figure out volume of those areca nuts. We are trying to see whether the CAD model we generate by hand, then after printing, we scan it and we see how much error is there. Like it won't be perfect. Whatever we modeled and whatever we get after printing, it's not perfect. So these kinds of study are being done using these 3D scanners and depth cameras in our lab. So these are one way to look into them, the error in 3D printing. 0.2 mm resolution. So 0.2 mm is the like least count you can say for. Okay, so we can close this.